next video for homework help, 27 and 28. One of these is pretty quick, not too tough. This one's a little more challenging. It doesn't take many steps if you know how to do it, but this one's a toughie. All right, so this one, I've got a whole mess of everything. I got secant, cosine, tangent, sine. I'm going to start this out, just change everything to sine and cosine. So 1 over cosine minus, if I've got a fraction over here, I may as well change this to a fraction. And then on the other side, this is going to be sine over cosine. Tangent changes to sine over cosine times another sine. All right, I've got two fractions. I'm going to try to combine them into one so it looks like this. Make a common denominator by multiplying this term, the second term, by cosine over cosine. Then I have 1 minus cosine squared over both denominators are cosine. On this side, I can simplify by saying it is sine squared over cosine. And hopefully at this point you're seeing where I'm going with this. 1 minus cosine is equal to sine squared. So this is sine squared over cosine squared. Now they're both the same thing, so boom, we're done. 28. This is, like I said, a tough one. This is one where I'm guessing when I made my answer key for this the first time, I probably spent 15, 20 minutes on it and went through half a dozen different approaches before I happened to do the right one. So, a couple of things here. You might be tempted to change everything to sine and cosine right away. And in theory, that would work. But it might get really long and ugly. And here's why I'm not going to do that. Tangent and secant are related through their Pythagorean identities. And I have things that are squared, or at least in even exponents, right? In fourths. And I've got a 1 over here. So it really looks like Pythagorean identities. And tangent and secant are nice together for the Taylor-Swift Pythagorean identity. The other thing that, and so, if I look over here, there's no Pythagorean relationship, at least right away, between secant, cosine, tangent, and sine. There's sort of like between cosine and sine, between secant and tangent, but nothing squared, so that's why over here I thought it'd be a better idea. I've got 4 different trig ratios. Let's get them all in sine and cosine. Over here, I just have the 2, and they're really closely related to each other. The second thing you might try to do is factor out secant from both of these, and that could work. And actually, what we're going to find out is I'm going to work on this side exclusively, and eventually it'll look like that. But that's not how I would start this either. I'm really going to focus on this side first, and it has to do with the fact that this is a perfect square, or it's a difference of squares. Excuse me. You might not recognize this right away as a perfect square. If it were 1 minus x squared, you maybe wouldn't recognize that as a difference of squares too, but it is. It would factor just like if it were x squared minus 1, except everything is in reverse. This would factor to 1 minus x and 1 plus x, right? Now, it's not x squared, though. It's to the 4th power. Well, this pattern is still the same thing. Any even power of x, if you take the square root of that, it's just half of the exponent, right? That's why raising to the 1/2 power is the same as taking the square root. So for 1 minus x to the 4th, it's going to be 1 minus x squared, 1 plus x squared. And if you FOILed this out and canceled combined like terms, you'd get to here. This factoring works. Well, it's the same thing with this one. So instead of 1 minus x squared and 1 plus x squared, it's 1 minus tangent squared and 1 plus tangent squared. Now, I have those split up. These are very, very similar looking to our Taylor-Swift Pythagorean identities, and actually this one is exactly it. 1 plus tangent squared is equal to secant squared. So right away, this one is exactly that. 1 plus tangent squared is equal to secant squared. So I can make this 1 minus tangent squared times secant squared. So I'm getting closer, right? I'm going to try to convert everything on this side into terms of secant squared, so it looks, or into secant, so it looks like this. Oh, shoot, I needed that. Okay, so really well for this side where it matched exactly, but what about this side? I can't get this to come out exactly from here, but what I can do, if I move this 1 over by subtracting it, tangent squared equals secant squared minus 1, I can change any tangent squared to a secant squared minus 1. So I'm going to do that with this tangent squared. This is going to become 1 minus secant squared minus 1 in parentheses. And that is very important because I'm subtracting, so what's on the inside of those parentheses, the sign is going to change for both of them. All right. So now if I simplify just what's in the big set of parentheses, it is going to be 1 minus secant squared, and then when I distribute there is a plus 1 times secant squared. And now 1 plus 1 is 2, so 2 minus secant squared times secant squared. Well, now I could either distribute the secant squared in, and now it's 2 secant squared minus secant to the fourth, or I could factor out a secant squared from both terms and get it to look like this. It doesn't really matter. So if I distribute in 2 secant squared minus secant to the fourth, and now they match. So we're all good.